Hello everyone, welcome to the lecture series on power electronics. In the previous lecture, we talked about the shortcomings that are associated with conventional multi-level inverters, that is the cascaded edge bridge inverter, the diode clamped and the flying capacitor multi-level inverter. In today's lecture, I would be talking about a special class of multi-level inverters which try to mitigate, or rather it hasn't got those shortcomings which are basically associated with the other conventional multi-level inverters. Just to recapitulate what are the various shortcomings. Number one is the large number of requirement of switches as we go up the number of levels in the output voltage. And for the three configuration, for the three topologies, classical topologies, the number of switch requirement was basically equal to twice of n minus 1, where n is the number of levels. So if n is large, then the number of switches becomes quite large. The second problem associated with the cascaded edge bridge, which was specific to cascaded edge bridge multi-level inverter, was the requirement of large number of DC power supplies, and as the number of level goes up. So, and that was equal to n minus 1 by 2. So, I had discussed in the previous lecture that DC power supply, if it is a battery or maybe any other source, is normally the costliest part of an inverter, inverter system rather, because it is inverter circuit. The source, DC source, basically reside outside the converter circuit. So let me say that inverter system has got the maximum cost. The maximum cost of the inverter system is because of the batteries. Then the shortcomings, two shortcomings, then the shortcoming that are associated with the flying capacitor and the diode clamp multi-level inverter was the higher number of capacitors required, and it was quite high in case of flying capacitor multi-level inverter. Rather, it was a quadratic function of the number of levels. So consequently, the control of the voltages of the capacitor poses a problem, which makes the circuit complex because of the requirement of the sensors to keep in to have a track on the voltage level, the voltage that is coming across the capacitor. So these were the shortcomings that were associated with conventional multi-level inverter. So that is why people have been developing newer topologies which try to overcome these shortcomings. And one of the topologies are called the switched capacitor multi-level inverter topologies. So switched capacitor multi-level inverters. As the name suggests, the capacitors in the multi-level inverter topologies are switched, that is, they are sometimes connected to the circuit and sometimes they are just cut off from the circuit, and thereby creating number of levels at the output voltage. So there are many topologies that have been reported in literature. I would be taking up one of the more famous topologies of SC-MLI, which is called the packed U cell inverter, in short PUC. Okay, and the name of this inverter is derived from the arrangement of the switches and the capacitor. Okay, so it is basically in U shape, and we will see that generalized version of the topology also exists. That means if we intend to go for higher levels, then we can extend this same topology just by adding U cells in cascaded fashion. Okay. Right now I have taken the basic version of the PUC inverter, and it involves 6 switches one battery and one capacitor. So let us try to see the operation. So I have drawn the switching, this is called the switching table. This is the switching table. So which gives the various states of the inverter output corresponding to the different states of the switches. Okay. So you could see that we have got 8 states in this PUC configuration, and corresponding to each state we have got a particular output voltage. So and you could see okay, so let's analyze this circuit. So we have got these 3 switches S1, S2, S3, and the other 3 S4, S5, S6 are basically operate in what we call in complementary fashion compared to S1, S2 and S3. That means S4 operation is complementary to S1. Similarly, S5 operation is complementary to S2. Okay, and S6 operation is complementary to S3. Fine. So that means we have to see only S1, S2, S3 in the table. Other S4, S5, S6 are basically complementaries of S1, S2 and S3. So let us see how this voltage V1, which is the battery voltage, appears across the output voltage. Okay. So in that case, S1 is on and S2 and S3 is off. So S1 is on. So I have drawn this circuit to show okay. So I have drawn this this same circuit here, and I have just left the state of S1, S2, S3, S4, S5, S6 as open, and I will try to fill it up corresponding to each of the state. So when state 1 is on, the output voltage is V1, which is the battery voltage. So in that state S1 is on, so that means I have to connect this. S1 is on, while S2 and S3 are off. That means S5 and X6 are turned on. Okay, and there is a battery here. So this is a battery, plus and minus, and the voltage is V1 here, and there is a capacitor here which is actually disconnected from the circuit for this particular state. Okay. So you could see here the output voltage that will appear across the load. Just you see the circuit gets completed by S5, S6 and S1 are involved in completing the circuit, and the voltage that is appearing across V0 is basically V1, which I have written it here. Fine. Now let us take the second state in which S1 and S3 are on. So if S3 is on, that means S6 is off. So if that is the case, then just see what is the output voltage that so we have to trace the path now from S3, and then we have to move through the capacitor through S5 and then through S1 and back to the load. So that means the output voltage that will appear across the load will be equal to V1 minus V2. Okay. So this is in state 2, second state. Fine. What about the third state? In S1 and S2 are on. So if S1 and S2 are on, that means S3 is off, and if S3 is off, that means S6 is on. Fine. So now battery gets disconnected from the circuit, and V2 is now providing the power to the load, and the voltage that is appearing across the output voltage is now equal to V2, and this is the third state. So, this is the third state. Fine. Now, state 0, 4 and 5 are state 0. These two states are 0 states. 0 state is one in which the output voltage is 0. So, either you turn on all the 3 switches S1, S2 and S3 and keep these off. So, output voltage is basically 0, or you keep these 3 open and short these 3 S4, S5 and S6, and that by short I means you turn on S4, S5, S6. So, in that case also the output voltage is 0. So, in the two cases output voltage is 0. Okay. So, that means you can get output voltage equal to 0 by two ways. Okay. So, let me pause here for a moment and tell you that this is one of the beneficial condition in a multi-level inverter when you get a particular level in the output by more than one way. So, that is called redundancy in that particular level. So, redundancy is at 0 level here. So, two ways of generating output voltage equal to 0. Next come to the next state, which is 6th state, in which S1 and S2 are off. S1 and S2 are off and S3 is on. So, S3 is on, that means S6 has to be off, and here S4 and S5 needs to be turned on because they are in complementary to S1 and S2. So, now the circuit you could see. Now, negative polarity of the plate of this capacitor gets connected to this point in the output voltage. So, now minus V2, output voltage is now minus V2. Okay. At this point, let me tell you one thing that let me tell you one thing about the state of the battery. Okay. Let me mention it here, the state of the battery, state of not the battery, sorry, state of capacitor. So, by state of capacitor I mean capacitor could either be in charging state, or it could be discharging state, or it is there is no change in the capacitor. Okay. So, you could easily see that when capacitor is only involved in the circuit, it is basically discharging. So, that means these two states, state 3 and state 6, in these two states the capacitor is discharging. That means the voltage that is appearing across the capacitor is coming down, while in these two states, state 2 and state 7, the capacitor is charging. So, you could see that this battery is in series with the capacitor, it is basically charging the capacitor. Let me see this 7th state and things will be more clear. So, in 7th state S1 is off, S2 is on. So, let us turn on S2. So, S2 is on, that means I have to turn off S5, and S3 is also off. So, S3 is off, then that means S6 has to be on. Now, you could see here, now the flow of current is like this, isn't it, through the battery and through this, and okay, direction has been reversed. If it is a purely resistive load, in inductive load definitely we have to see whether it would be in this direction or not. Okay. And but one thing is very clear, that the capacitor is charging. It is in series with the battery and it is getting charged. So, that is why I have written C here, charging in 7th state as well as in 2nd state. And in 8th state you just check, it will come out to be minus V1, that is battery is getting connected across the load in reverse fashion. So, this is how this circuit operates. Okay. Now let us see what are the benefits associated with this particular packed U cell inverter, and what are the advantages that are associated with it compared to the conventional inverters. So one very apparent advantage is that it has having only one battery. Okay, so you must be telling okay, then how many levels are being generated in this particular case. Acha, one thing just I forgot to mention about the levels in the output voltage. So if I am keeping V1, let me write it here. So if I am keeping V1 equals to VDC and V2 equals to VDC by 2, okay, then what will happen? So that means this will become VDC, this will become VDC by 2 plus, of course, and V2 is again plus VDC by 2. This is 0, this is 0, this is minus VDC by 2, this is again minus VDC by 2, and this is minus VDC. So how many levels you could see? VDC, VDC by 2 and 0, and minus VDC by 2 and minus VDC. That means 5 levels. 5 levels in the output voltage. I am not talking about, I am just talking about the output voltage levels. So 5 levels are being obtained if we keep this V2 equal to VDC by 2. Okay. So how to keep this VDC V2 equal to VDC by 2? So you could see here that in case 2 or state 2 state 3, again we have got this redundancy, output voltage is equal to VDC by 2. Similarly in 7 and 6 and 7 we have got this redundancy when both the output voltage is equal to minus VDC by 2. So we can exploit this redundancy and serve our purpose to maintain the output voltage of the capacitor or the voltage appearing across the capacitor equal to VDC by 2. How? So if we select charging state, okay, when we are generating plus VDC by 2 output voltage, and we select discharging state, that means 6th state, when we are generating minus VDC by 2, that means in positive half cycle capacitor is charging and negative half cycle the capacitor is discharging. So the net change in energy is 0 in one complete cycle. That means the output voltage of the capacitor will remain fixed at VDC by 2. Okay. So that is the special property of this packed U cell inverter, in which the output voltage for 5 level PUC, the capacitor voltage is inherently balanced just by judicious utilization of the redundant states. Fine. But say we want to enhance the voltage levels. So if we take this V2 as VDC by 3, okay, then what will happen? So here the voltage level now become, this is VDC by 3 and this become VDC by sorry, it is plus 2 VDC by 3 and this is VDC by 3, then here also minus 2 by minus 2 VDC by 3 and this is VDC, and here it is VDC by 3. Now you could see here 0 VDC by 3, 2 VDC by 3 and VDC by, that means 7 levels. 7 levels could be generated if we could keep the capacitor voltage equal to VDC by 3. 7 levels are, and correspondingly the configuration is called PUC 5 or it is called PUC 7, depending on the levels in the output voltage waveform. Okay. And that depends on what is the voltage of the capacitor. So if it is half of that of battery, then we get 5 levels output, and if it is 1/3 of that of battery, we get 7 level output. Okay. But the issue with 7 level is that to we see that to maintain VDC by 2 voltage of the capacitor, it is quite easy just by selecting judiciously the charging state in the positive half cycle and the discharging state in the negative half cycle, we can easily maintain the capacitor voltage equal to VDC by 2, but it is not the case when we try to keep the output, when we try to go for 7 levels. Therein we have to keep the capacitor voltage equal to VDC by 3. So, the situation now here is a bit difficult, okay, because you see in charging, during charging, when capacitor is getting charged, the level of voltage is 2 VDC by 3 when I am trying to generate 7 levels output, and in the discharging state you could see the level of the output voltage is minus VDC by 3. So, there is a difference in the levels in the positive and negative half. That means we cannot just without any control keep the voltage across the capacitor equal to VDC by 3. There is no inherent mechanism in the switching state, although there are and because of the there is no redundancy in the levels, okay, apart from this 0 level there is no other redundancy. So, that means because of this we cannot actually obtain a 7 level PUC inverter which is having self voltage balancing capability of the capacitor. Okay. So, this is one issue. So, that is actually taken care of by using some sensors, voltage sensors across the capacitor and trying to maintain the voltage equal to VDC by 3. So, that can be done. Okay. But the important thing is that we can obtain 5 level output without actually caring about the voltage balancing problem of capacitor in 5 levels. Okay. Now, one thing I was trying to tell you that we can extend this circuit to n levels. Okay. How we can do that? So, what basically we have to do is to just add U cells. This U cell, okay, or if I want more levels, then one more U cell. So, okay, and so on, and this gets connected to the last unit. So, I am just enhancing voltage level by adding this U cell in the existing inverter configuration. Okay. You could see that quite modular nature of this inverter, and we can now generate large number of levels in the output voltage by generalizing this circuit. And interestingly, the output voltage level for n plus 1 cell, one cell is this 2 switches and 1 capacitor. So, if we have got n plus 1 cell, then the output voltage level is given by n into n plus 1 by n into n plus 1 plus 1. So, this much levels can be generated. Just you see that there is a quadratic rise in the number of levels with an addition of cell in this configuration. Okay. So, basically if I try to plot it, if this is the number of levels on the x axis and this is the switch requirement switches, so it increases actually exponentially. Okay. Exponentially compared to the configurations of the diode clamped or cascaded edge bridge or your flying capacitor, in which the rise is linear. There is a linear rise. okay, and that is 2n plus 1, I think, 2 into n, oh sorry, 2 into n minus 1, something like that. So, as the number of levels increases, for a lesser number of switches, the number of levels get increased manifold. So, this is one of the advantage which we are getting in by using this packed U cell inverter, that at lesser number of switches, with lesser number of switches, we are generating large levels in the output voltage. Similarly, we have seen that for 5 level, there is a self balancing capability in the voltage balancing capability in the circuit, just by judiciously selecting the switching state. Okay. So, I think you have understood the operation of a packed U cell inverter. These inverters have become quite famous nowadays, and lot of research has already been done on this inverter, and it has been used in variety of application, and even for grid connected operation also it has been tested. So, this is a promising, this topology is a promising, has a promising future. Okay. So, I thank you for watching this video.